data transmission. So in this lesson, we're going to be looking at network switching. And to start the ball off, if we look at our lesson objectives, the key thing here is for us to be able to explain the difference between circuit and packet switching. Describe an appropriate network protocol such as TCP, IP, and the contents of a packet on that network. What you can see there is a diagram, and basically if you consider the internet, it's a collection of networks all connected together, and the aim is we can actually navigate that network by using circuit and packet switching. These are two methods that's used to send data across the actual network as such. If you consider, I'm trying to get from point A to point B, the start and end. If I was to ask a driver to actually go from start to the end, the driver may decide to choose any path, and that's basically how we send data. Now, if we look at traveling across the network, they have highlighted two different paths. It doesn't really matter how you get from point A to point B, but traveling across the network, if we consider how circuit switching works, the way it works is this. When we make a connection or electrical path from one point to the next, once the path is established between one computer and another, that path will remain established throughout the whole communication time. You will be sending data continually, and for any reason, it's sent via the computers. Each packet is sent one after another, and potentially, if we have a problem, then we'll potentially re-establish the communication. An example of circuit switching is a telephone network. So someone goes to make a call, a connection is made, and it's routed via a series of computers. Whilst you're talking, that line is busy and no one else can actually get through on that line. Now, if the connection fails, then we have to reconnect. Now, the fact of the matter is, as we're sending data, and as with normal speech, there's a pause built in. And whilst there's a pause, there's no data being sent. So basically, that is a somewhat inefficient type of network. Now, if we consider packet switching, now with packet switching, and this is where I'm now going to play a video.
7, 6, 5, 4, 3, 2, 1.
Hi, my name is Lynn Root. I am a software engineer here at Spotify, and I'll be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. But how is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify. It seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct, dedicated connections, it would be impossible to keep things working as millions of users join, especially since there is no guarantee that every wire and computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times, but once all the pieces are there, you can reassemble the pieces into the complete shuttle and it'll be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits or ones and zeros, too many to send along in one packet. Since it's data on a computer, the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the Internet Protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address for the packet. Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly wrong. This is the basis for a key principle of the internet: reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. How can you be 100% sure all the data will be delivered so the song plays perfectly? Introducing your new best friend TCP, Transmission Control Protocol. TCP manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgments of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the internet becomes. What's also great is we can grow and scale the internet without interrupting service for anybody using it.
The internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the internet connect to each other, communicate with each other, and work together because of agreed upon standards for how data is sent around on the internet. Computing devices, or routers along the internet, help all the packets make their way to the destination where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the internet talk to each other.
So, in terms of packet switching, what does that mean? Well, basically, the packets themselves, they take independent routes throughout the network. And the aim is each packet decides, like in terms of a driver, to actually take his or her own route, and it navigates its way through. And depending how loaded or congested the actual pathways are, it will actually adjust its route to suit. Now, in terms of communication, packet switching is more resilient. So if we have a blockage or failure between one link or another, if it's brought down, the packets can actually just automatically find another route and navigate its way through, making it more efficient, more intelligent, and ultimately more resilient, which is what the internet is based upon. So ultimately, the packets themselves have an issue. If each packet is taking its own route, then there's extra processing needed because the packets won't automatically arrive in the correct order. Whereas with circuit switching, you're sending data serially, whereas packet switching, we send you all off to say, go away, find your own route, and then when you reconvene, we have to reassemble the actual final message. So each packet has to be labeled with an order number, and the destination PC has to keep track of each packet as it's come through, tick them off, as you saw with the Spotify there. And as they go through, the data coming through, it's more efficient on the bandwidth because no part of the network is actually reserved, so you can take any route you want, and every link in itself can be shared by multiple connections. So how does that affect us in terms of a protocol? So TCP/IP is one such protocol. It's a protocol which is a lot more common, and it's used in LANs and WANs, and you should know what that is: local area network and wide area network, including the internet. And the TCP portion of the protocol performs the handshaking, so the communication, the packet sequencing, the flow, and the error handling to make sure that the data is sent securely. The IP allows the messages to travel from one part of the network to the other, so it manages the actual route and destination IP addresses as such. So what does one of these packets look like? Well, ultimately, if we look at a typical TCP/IP packet, it has some form of structure to ensure that the packet's delivered. You're going to have some sort of a header, which is required. The source address, destination address, i.e. where it's coming from, where it's going to. The TCP header, a sequence number to say, okay, where does this packet fit in with the rest of the packets? The data itself, what you're actually sending, a checksum, a little bit of a calculation to make sure that none of the bits or bytes or even that down to the minuscule bit of data is lost, and some tracking information which basically gives some information of the route it's actually taken. So ultimately, when the packets are sent, you can see that the packets go through, they resemble something similar to what we've got displayed there, and that's really how a TCP/IP packet what it looks like as such. Now, what do we want from you? Well, in terms of the examiner, you need to be versed in a position where you can compare and contrast the different types of packet switching, whether it be circuit or packet. You need to be focusing on, in your response in the exam, on the fault tolerance, how reliable it is. Obviously, you know the issues we've got with circuit, you know the issues we've got with packet, how the routes are established, bandwidth, how efficient does each actual switching network have on the actual bandwidth, and the packet order delivery. Part two of the actual response that I need you to work on is the term checksum. Find an example, explain what we mean by the term checksum, and the general term switching. So when they talk about switching, that can include both circuit and packet, but what is the term switching? So get yourself a definition for that, and armed with that, you should be well versed in answering any question the examiner can actually send at you.